party.
Okay.
I hope you don't call the police. I'll be talking about exact bulk operators and the fate of locality. This is work with these people, and I mean, there's a paper that hopefully will be out in another month. This is designed to be a short talk, but you can interrupt me and ask me lots of questions and ask me to explain things in more detail, and we can make it a longer talk. Okay, so the general goal of the program is to try to understand the black hole information paradox. And what do we mean by that, or what is sort of, how do we break the black hole information paradox into some series of sub-problems that we can address and make progress on and creep our way towards the solution. I think more generally, I'm interested in any examples where there are qualitative disagreements, between the predictions of gravitational field theory, or maybe perturbative string theory in anti-de Sitter space, and the predictions that follow from some exact unitary conformal field theory. Now, importantly for the way that I tend to think of the exact definition of ADS quantum gravity as being the conformal field theory. You might hope to have some exact bulk definition and an exact conformal field theory definition, but thus far we don't really have that, and so I'm assuming that the sort of ultimate arbiter of truth is this conformal field theory, and that we have to define anti-de Sitter physics, black hole physics, etc., using conformal field theory. So that means immediately there are two classes of observables that you can study. You can study observables in the conformal field theory itself, or you can study observables in anti-de Sitter space. Now, of course, if they're just supposed to be the same thing, ultimately these should be related, but I think there's a sort of major conceptual difference. If we talk about observables in the CFT, it's very, very unambiguous what we are actually talking about. The CFT just makes a prediction directly for its own observables, and we can use the ADS CFT dictionary to compute something in ADS and extrapolate it to give it a conformal field theory observable, and we can compare these things. So problems associated with these CFT observables I think of as being easier because we know ultimately, we ultimately know what the right answer has to be, and so the only problem is to understand what's missing from gravity and anti-de Sitter space that's causing it to disagree with conformal field theory. And there are a lot of examples of these kinds. Since I only allotted 30 minutes for the talk, I can just go on and on about them. Two or three known examples are, there's this problem that Maldacena first pointed out in, I think, 2001 for eternal black holes, which is that if you study a two-point function separated in time in the background of a black hole in anti-de Sitter space, then if you look at very, very, very large time separations, this observable goes to zero. It decays exponentially, and it becomes arbitrarily small. Now, what is this observable doing physically? Well, you're pinging the black hole by acting with some operator in the CFT, and then you're sort of reading out with that same operator how much of the signal is left at late times. So the fact that this signal decays exponentially out to arbitrarily late times can be viewed as a kind of indicator of information loss, because the black hole is just kind of completely swallowing all of this initial perturbation. And this is actually a violation of unitarity in a theory with a finite number of local degrees of freedom living on a compact space. And the CFT in this case is living on a compact space because it lives on a circle. You're studying ADS CFT in global coordinates. So that's one example of this kind of problem. There's another example that we studied in the past, and that I'm purposely excluding from this talk because it's prior work that I've gone on and on about before, which is an indication of the fact that black holes have a temperature. So in quantum field theory, in actually just any quantum mechanical system, a way of understanding the fact that you have a finite temperature in your correlation functions is by looking at their behavior under Euclidean time continuations. So there's this thing called the KMS condition, which basically says that thermal observables, observables at finite temperature in the canonical ensemble, are periodic in Euclidean time, with a period set by 1 over the temperature. So you can look at that periodicity. You can look for that periodicity. Now, in a pure state, an exact pure eigenstate of the Hamiltonian with very, very high energy, you would expect that observables should be approximately thermal. There's this idea called the eigenstate thermalization hypothesis that very, very high energy pure states should be very hard to distinguish from thermal states. However, they can be distinguished from thermal states at some level. And in particular, correlation functions in some high energy, in some pure high energy state shouldn't be periodic in Euclidean time. They might look like they are approximately for some analytic continuation, but this periodicity should break down. And that's another way of studying the difference between pure states in conformal field theory and the kind of data that you get from studying quantum gravity. Because if you write down a black hole solution in any space-time, but I mean in particular in ADS, just by the very structure of the black hole geometry, if you look in Euclidean time, you have a periodic geometry, which means if you do any calculation in the black hole geometry, you'll see what looks like thermal physics. And no matter how high you go in perturbation theory, to however many orders, you'll always see thermal physics. So that's another example. This is an example of something that you could address by just studying observables within the CFT. You can compare what you get from a black hole background in the CFT to, what you get from a black hole background in ADS and what you actually get exactly in the CFT. And you can understand how there are non-perturbative effects in G Newton that sort of resolve these kinds of problems. So I'm not going to say anything more about that, but I just figured I would mention it since I probably have extra time. The kind of problems that I want to start to address in this talk are harder problems conceptually because they involve actually asking about what's happening in anti-de Sitter space deep in the bulk at finite distances, hopefully eventually near black hole horizons. And these problems are harder conceptually because we have to somehow define how to reconstruct what's going on in anti-de Sitter space from the conformal field theory. So this is a picture of such a reconstruction. Given CFT data that we have at our fingertips, we want to try to reconstruct what's going on in the much more glorious regime of the bulk. And so the kind of questions that we would like to address to really talk about the black hole information paradox in ADS CFT are how to define bulk reconstruction in some exact way, not just in perturbation theory, not just in some approximation that already assumes we have ADS gravity, and to try to figure out whether there are any limitations on this, and if so, what are the quantitative limitations on this reconstruction of ADS observables. And then this is really the first step to eventually then ask, what do local observables do near and across the horizon of a black hole? And the reason why you want to ask this question is that the black hole information paradox is this tension between the unitarity of quantum mechanics and the locality, the equivalence principle in general relativity. And it's easy to give up one of them and it's easy to give up one of them. So when we study, say, the Hawking evaporation process, we assume everything's local. We have usual effective field theory and locality near the horizon of a black hole, and we get this prediction of thermal Hawking radiation. Conversely, in ADS CFT, we have an exact unitary CFT, so clearly no information is lost, but it's not at all obvious from the point of view of the CFT what's going on near the horizon of the black hole. So in this ADS CFT context, the way I think the thing we have to do to resolve this paradox or understand what happens with it is to be able to probe near black hole horizons. Okay, so then the general question I want to try to address in this talk is, given some CFT, is there some exact prescription for local quantum field operators in the dual ADS spacetime? And if we have such a prescription, what do we want it to do? Well, we have to specify where in the bulk this field is located. I mean, fields that we think of as local fields have phi of x. We have to define what we mean by x. All of the correlation functions of this field that we define should match bulk perturbation theory in any semi-classical background. So we should have some phi of x. We know where phi of x is in any semi-classical gravity background. And we can also treat general relativity as an effective field theory, expand in G Newton, and compute loops, whatever we want. And we should match our prescription with perturbation theory. They should agree. And third, we should have some quantitative prediction about the regime of validity of our definition of bulk fields. So there's all sorts of lore based on black hole thermodynamics and the fact that general relativity is a gauge theory, and thus space-time seems like it's gauge redundant. There's all sorts of lore that bulk locality cannot make sense at short distances, maybe not at all, in quantum gravity. So we'd like to see quantitative predictions of what happens with bulk locality. So what I'll show in this talk is that we can actually solve this problem using in a very pretty general way by taking advantage of the Virasoro symmetry in ADS3 CFT2. The result is something that I'll refer to as an exact bulk proto-field. It's a proto-field because it's not a full field in a full theory, but full fields and full theories aren't necessarily sums of these proto-fields, linear combinations of these proto-fields. When you have something that's entirely determined by symmetry, it's sort of agnostic about what theory you're talking about, so different theories might have different coefficients for different linear combinations of these objects, but these objects are really just forced on you by symmetry. If you don't want to remember any of those words, this is really just equivalent to studying what you get by trying your best to have a free quantum field coupled to gravity in anti-de Sitter space in 2+1 dimensions. So really, instead of calling it a proto-field, you could just think of it as the best you could do at getting a free field coupled to gravity. And then I'll tell you that we can compute the two-point function of this proto-field exactly in various ways, again taking advantage of Virasoro symmetry and various sort of fancy related two-dimensional CFT techniques. And we'll find some non-perturbative effects that seem to show the breakdown of locality due to some violation of unitarity at short distances. So we'll find quantitatively how bulk locality breaks down. So before getting to the full story, let's solve a warm-up problem. So let's just talk about bulk reconstruction without gravity turned on at all. This is also a problem that we can solve by symmetry. We can solve it exactly. It's well known. And so let's do it, but in a slightly different way than is usually discussed. So the simplest observable in ADS CFT, I think, of all, is the bulk boundary two-point function. There is a field in ADS, there's a CFT operator, and this answer is completely guaranteed by symmetry. So I wrote the answer in this way because it makes it clear that it's guaranteed by symmetry. This is in what's called the embedding space formalism, where conformal symmetry acts linearly as a D plus two-dimensional matrix. And so this P dot X is the only thing that's invariant under multiplying by that matrix on P and X. So this makes it very clear that it's defined by symmetry. You can write this in some explicit coordinate system. So for example, in the Poincare patch, this is, if I write down the Poincare patch metric, just to make this extremely explicit, y is so y equals 0 is the boundary. Then this is just y to the delta over y squared plus zz bar. Anyway, this is the exact bulk boundary two-point function. But if you're a person who likes to think about conformal field theories in a kind of quote-unquote bootstrappy way, in particular if you like to think about radial quantization, then what you can notice is this correlator actually immediately tells you how to decompose phi in terms of the primary operator O and all of its conformal descendants. In other words, if I think about this picture where I have phi over here and say O over there, then I can draw some really, really big circle in the CFT around phi. I mean, phi is really off at ADS, but just ignore that. Imagine it's pretty close to the boundary. I draw this big, big circle, and I want to decompose this correlator into states. So I have a sum over all states in between phi and O. If I do that, the only states that can ever contribute to a two-point function between O and something else are O and its conformal descendants, right? I mean, if I have two different CFT primaries, their two-point function is always 0. So only this primary can be contributing to the sum over states. So the only states that contribute in the middle, in other words, if I think of decomposing on states in this circle, the only states that contribute are O and its descendants. And then just by expanding this correlation function in, say, Y, I can read off what the coefficients are. This is the same way that in the operator product expansion, you can read off OPE coefficients. If you have a three-point function of a CFT, you've probably seen this. If I have O1 and O2, and I draw a circle around them, and then I have some O3 over here, I can read off what the decomposition of O1 and O2 is into descendants of O3 just by expanding this three-point function. It's even simpler here. I just expand the two-point function, and I get an expression for phi in terms of descendants of O. So, go ahead, yeah.
Sorry, I'm confused about something basic here from the start.
Yeah.
Is that expression does not look diffeomorphism invariant. I mean, you're, okay, but
So,
it should still be diffeomorphism invariant, though, shouldn't it?
I don't know. I mean, why don't you ask me about that if you're bothered by it when we talk about Virasoro? So in Virasoro, I mean, just to tell you the answer, I'm going to fix a gauge and fix what coordinate system I'm working in, and that will be how I define my field. So the answer will not be diffeomorphism invariant, and in fact, choosing a different gauge will give you a different bulk operator. Here, this is all just kinematics without gravity. But you can ask me more, and we can discuss when we talk about gravity. So there's an equivalent way of saying everything that I just said on the last slide, which is instead of studying this correlation function, this two-point function, you could just talk about symmetry. So without gravity, if you do ADS CFT without gravity, you don't worry about diffeomorphisms or anything. There's just some fixed pure ADS metric, like this one. Then the whole point of ADS CFT is supposed to be that the isometries of that metric correspond to the conformal transformations of your conformal field theory. So what that means is that all of the conformal generators should act on a bulk field that's labeled by some point in space-time as the corresponding ADS isometries. Now, I'm going to write, anticipating what I just said on the last slide, that phi is a linear combination of descendants of O. I'm going to write phi as some infinite sum of descendants of O with various powers of y. So y is the sort of radial direction, z and z bar are the direction in the plane of the CFT, and I'm writing this expansion. Now, by writing this expansion exactly this way, I've actually already anticipated many features of the answer. You don't have to, but that's simpler. So I've done it. What we want to do now is demand that under conformal transformations, phi acts as though it's a bulk field. So what that means is that when I act with any of these conformal generators on this object as a quantum operator, they act via these differential operators or bulk vector fields, which are supposed to be the generators of that symmetry. So for example, L-1 is just translations in the plane, and so this is just ddz, and that's automatic. L-1 commutes with all of these things that are written here, and so that just happens automatically. L0 is something that we can work out more directly. Given that we have this expansion for phi, right, I mean this is O and its descendants, we can act L0 on sort of both sides of this expression. We want z dz plus 1/2 y dy when acting on this side. And that's guaranteed by the fact that L0, when it acts on this expression as a quantum operator, it just knows about L minus 1 and L minus 1 bar and O. And in fact, all it does is measure the number of n's here. And so it gives you this translation part, but it also gives this, it's supposed to give a factor of n. And that factor of n comes either from the commutation relation that, so L0 on L minus 1 is L minus 1. So you can use that commutation relation to act L0 on this expression here. And that gives the same result because it just gives you a 1 for each of these L minus 1s as acting with 1/2 y ddy, because 1/2 y ddy brings down a factor of 2n times 1/2, which gives you an n. So you can check explicitly that this expression creates a bulk field with the right symmetry transformation properties if this coefficient in the sum takes this form. And to exhibit the fact that that coefficient has to take that form, you act with L1. So L1 is more complicated. It connects n and n plus 1 and gives you a recursion relation that tells you that this has to be a coefficient. Now, this is all just a warm-up to tell you about how you can do bulk reconstruction in this kind of expansion in the bulk distance y. This is all entirely equivalent to things that you may have heard of. There's, it goes back to the early days of ASCFT, but there's this thing people refer to as the HKLL kernel, where you take the operator O in the CFT, you multiply it by some function, and you smear it, you integrate it over something, and get a bulk field. This is exactly equivalent to that formalism, and just a rewriting of it in this expansion in small y. So, any questions about the warm-up? So this is mimicking a boundary operator expansion. So if you're someone who really loves all sorts of stuff about CFTs, you may have heard that you can study conformal field theories with a boundary, and you can expand operators in the CFT in terms of operators on the boundary. That expansion is exactly this kind of thing. Okay, so the lessons from this warm-up are that you can use symmetries to just directly determine a lot of stuff about what bulk fields are supposed to do. And that's exactly equivalent to defining the bulk fields by thinking in terms of radial quantization if you know the bulk boundary correlation function. So if you know, here we knew the bulk boundary correlation function by symmetry, and so then we were able to do this decomposition. But if someone hands you the correlation function of some bulk field phi with a ton of other CFT operators, you can try to decompose it in this way. So those are two methods. Both of them are going to generalize to the ADS3 CFT2 case with Virasoro, and so that's why I mentioned that. And note that this is really just a bulk proto-field. So in the case of our warm-up, this is really how you can define something that acts like a free field theory in ADS space. Not an ADS space with gravity, but just ADS space in any number of dimensions. It has the right correlation functions to be a free field. Really, full fields in some fully interacting theory should be some sum, presumably an infinite sum, of these kinds of primitive objects that are fixed by symmetry. And that's what, there's a whole long series of papers by Cabot and Lifshitz and others that develop this point of view, and they sort of show how in perturbation theory you can figure out what those coefficients are, etc. Okay, so now we want to do the same sort of thing with gravity, taking advantage of Virasoro and ADS3. So just to emphasize why we can deal with gravity, roughly speaking, we like to say in ADS CFT that the bulk gravitational field is dual to the stress tensor in the CFT. Furthermore, in two-dimensional CFTs, the stress tensor can be decomposed in a mode expansion in terms of operators ln. These are none other than the Virasoro symmetry generators. So what that means is that Virasoro symmetry generators act on the vacuum and create things that you could call graviton states. Now, what that suggests is that if you know a lot of stuff about the Virasoro algebra, then you know a lot of stuff about quantum gravity, and even that multi-graviton matrix elements are fixed by symmetry in ADS3. So this is very different from higher dimensions. In higher dimensions, you don't have this wonderful advantage. But in ADS3-CFT2, Virasoro symmetry basically determines how quantum gravity works. And you can see this very explicitly. So related to the sort of easier problems I mentioned on the first slide, you can compute things called Virasoro conformal blocks that encapsulate all of the combined contributions of everything related to everything else by Virasoro symmetry. And for example, the vacuum Virasoro block at large central charge takes this simple form. It knows about the Hawking temperature of a BTZ black hole very explicitly in its structure. And so this is really just motivation that by using Virasoro we can incorporate the effects of quantum gravity. So, as I guess Brown and Hinault showed, in ADS3-CFT2, Virasoro acts as an asymptotic symmetry. This only identifies what Virasoro transformation should be with some equivalence class of diffeomorphisms that vanish, but that don't vanish very fast as you approach the boundary. But this is really just some equivalence class of diffeomorphisms. You can do whatever you want in the middle of the bulk of the theory, and all that really matters is the asymptotic behavior of these diffeomorphisms. And that's hard to work with. However, if you fix a coordinate system, which in general relativity means fixing a gauge, then you can fix exactly what the diffeomorphisms are supposed to be. So if I choose to study metrics of this form, so I think sometimes they're called Vannados metrics, you could also think of them as vacuum metrics. If I choose to study metrics that take this form, then I can figure out how the Virasoro transformations act in the bulk. Because the Virasoro transformations are supposed to be the diffeomorphisms that just preserve this gauge choice, that turn a metric of this form into another metric that can be written in this form, maybe with a different function s and s bar. These are also, the reason why I call them vacuum metrics is that these metrics can be obtained by taking the vacuum of ADS and acting with some Virasoro symmetry. So we're going to be working in this gauge, in this coordinate system, and that's an important choice which will have consequences throughout. So we found what the infinitesimal transformation rules in that metric are, what the infinitesimal Virasoro transformations are, and how do these Virasoro symmetries act on a scalar field? Well, the whole point of a scalar field is that it transforms as a scalar, which means that under some space-time symmetry, it goes to itself plus some delta y times dy plus delta z dz plus delta z bar dz bar acting on phi. That's what we mean, I think, by a scalar field. Now, we figured out what these deltas are supposed to be, and this is the formula for any Virasoro transformation Ln. Now, the ultimate, these formulas are somewhat complicated. The ultimate physics of this is actually very simple. So notice that if you look at each of these formulas, for m bigger than or equal to 2, all of these vanish as z goes to 0. That's just because we have a z to the m, a z to the m minus 1, and a z to the m minus 1. What does this mean physically? Well, you could think of these LMs, I mean, these LMs are some sort of infinitesimal space-time transformation. What's really going on here is that as z goes to 0, these all vanish. So these LMs with m bigger than or equal to 2 just don't move the origin. I mean, we have this definite coordinate system that I wrote on this slide. There's a special point z equals z bar equals 0, and we're kind of expanding around that point, and these Virasoro transformations don't move the origin, even at finite y. So even as we go off into the bulk, they don't move. So that's really all the physics of that rule. So this leads to a definition. So we're going to do the same kind of ansatz that we're going to use the same kind of ansatz as we used in the warm-up, except now we're going to allow completely general polynomials in the Virasoro generator. So these script LNs are any polynomial in all of these different Virasoro modes. So these in general can be very complicated. I'll show you one in the next slide. And we want to take this ansatz and impose on it the symmetry consideration. So we have this bulk primary condition that these LMs with m bigger than or equal to 2 have to annihilate phi if phi is at the origin, if phi is at z equals z bar equals 0.
So,
Yep.
I'm sorry, can I ask a question? I should be able to describe these. So the Virasoro generators are well defined on the boundary, but you made some kind of a prescription to say what they do in the bulk.
Yes.
And you gave a formula for that.
Yes.
So I can't complain. But I want to know, is there some way of describing sort of geometrically what that prescription is? In other words,
I mean, there is.
You know, you see what I'm asking?
Well, I mean, I think so. I mean, I think the prescription is that infinitesimally you can write down a vector field in ADS that is generated by this transformation, and so you could draw infinitely many vector fields labeled by m that look like this infinitesimally, and that's what we're learning. Those are supposed to be the vector fields that infinitesimally preserve this gauge choice.
Right. I'm just saying that's not very transparent. Is there another way? I mean, this is not transparent at all to me. You know,
Sure.
there are formulas, and I can't complain. But
so
as
as I've said and as was asked, I mean, this depends on your gauge choice. I mean, and I don't think there's any way of escaping that conclusion.
Right,
This is going to depend on your gauge choice. This gauge choice is very natural. I mean, there's this thing called the Pfefferman-Graham
right.
condition. This is basically the Pfefferman-Graham condition. I mean, it's something that very naturally, I mean, you have the boundary metric, you have these pieces which, as you approach the boundary, these would be interpreted as the VEV of the stress energy tensor of the CFT in this space-time.
The extrapolation in my language is the fact that these S's don't depend on Y.
Yeah.
Or trivially they have this Y.
Yeah, there's this Y² thing in the mixed term, but yeah, these things give you the VEV of the stress energy tensor. But yeah, I mean, you can choose it. You can choose a different gauge, and you'll get something different. And I mean, I don't know what to tell you. I think this is a very natural choice. Like, I think probably it's just a theorem that this part of the metric is guaranteed as Y goes to 0. But then I think the rest and what happens at finite Y, you could have chosen anything, and I've chosen the simplest thing. And I mean, it's important, but yeah.
So, but that expression is assuming that the metric satisfies the exact Einstein equations. The dependence of Z and all that. So you're assuming that there's no back reaction.
Well, we're going to be so this is kind of a subtle question, and I think I know pragmatically what happens better than I know sort of a general beautiful theory of what happens. So you might think that I call this a vacuum metric. I said it's sort of like what you get in the vacuum or the vacuum with Virasoro. Now, given that statement, it might surprise you that the BTZ metric for a BTZ black hole also can be written in this form. I mean, not you probably, but it might surprise some people. So the point is, I mean, if say you have some finite number of particles that are sort of moving around in ADS, but they're really sort of giving you some delta function contribution to T mu nu, then this form would be violated sort of on the trajectory of the particle. But as long as there's sort of as long as that's all that's happening, basically you have some pole in these functions where that particle is, and sort of that's it. So this sounds like it's fairly restrictive to just the vacuum, but really it seems to be general enough to encompass kind of the vacuum plus any number of particles or something like that. Certainly it's enough to study BTZ black holes, which is what we would eventually in sort of the second or third from now paper like to address. So
this is so. I mean, isn't it true in 2D? This is. Sorry. Once you satisfy the Einstein's equations with negative cosmological constant, you're locally ADS2. Is that correct?
Sorry, you mean locally ADS3?
3.
Yeah.
ADS3.
Yeah.
Sorry,
Locally you're
Right.
ADS3. So, but I mean, you might imagine you could have like a gas that like is like a fluid filling space, and then this is just sort of totally wrong. But if you just have a few particles, then it's locally ADS3 everywhere except at where those particles are. So yeah, that's why I say. I mean, I don't know what the sort of beautiful theory is, but I mean, this seems to work even when you have, say, a heavy source that creates on a line a violation of this. So anyway, I mean,
But it doesn't work when you have a scalar field.
Well,
It's,
good.
I mean, it's
So
not a solution of.
it's not a solution. It's a classical scalar field, absolutely.
Yeah.
So the question is,
So-
so what I would say is that, I mean, I want to think about the system as ADS-CFT is just some quantum system. I don't ever have a in the quantum theory. I don't have a classical field profile. I have some set of particles, and what we would like to understand is whether or not this this does apply even for some quantum correlation function, and I mean that's what we'll be doing in the future. Here we're just going to be studying the two-point function of a scalar field.
I mean, the reason I'm worried about this is that in this setup there isn't anything to Hawking radiate.
Oh, well that's fine. So I mean I'm not going to study Hawking radiation in this talk.
Yeah, that's fine. But
Yeah.
It's
So
a limitation.
so I mean maybe at the end I can tell you what I think we're going to do that will be the interesting thing to do. But yeah, for now I mean I'm not going to talk about Hawking radiation in this talk anyway. I mean the basic point is that I want to study the two-point function of a scalar field in the background of a black hole that just sits there forever. That black hole is just created by some CFT operator at the beginning of time and destroyed by it at the end of time. And that four-point function decomposes into conformal blocks. I can sort of compute all of those. Anyway, so that's sort of the philosophy. But okay, so I told you that we get this condition. It's a new condition. It's a primary condition. It's algebraically very simple. And then there's one more condition that you need, and it uniquely determines phi, uniquely determines all of these things and this coefficient, which is that in the limit, I mean, this most physical way of saying it is that in the limit that the central charge goes to infinity, so gravity goes away, you get back the answer for a global field without gravity. There's some normalization condition, basically, that this requires, and this condition plus this condition uniquely determine what phi is algebraically exactly. So when I say exactly, I mean exactly in G Newton, not in perturbation theory. So for example, the simplest non-trivial script L minus n is n equals 2, and this is just the formula for what the answer is. So it's a linear combination of L minus 1 squared and L minus 2, two Virasoro generators. And this is the central charge, and h is the dimension of the operator dual to the scalar field. So 2h times 2h minus 2 is the mass squared of the scalar field in the bulk. So you can see this is not, I mean, a perturbative expression in C would have some expansion of 1 over c to the n. This is some exact thing. Great. So what that means is I can calculate correlation functions of this field, and it will know about non-perturbative gravity effects. Now, I'll just say this briefly. This is all equivalent to, this can all be obtained if you know all correlation functions of this form. So I said there are two ways of determining a bulk field. One is by symmetry. The other is if you know correlation functions, you can just decompose. Previously, we had this without any of these things, and we got the global case. If you know the correlator of phi with a CFT primary and any number of stress tensors, then you can decompose phi into not just global descendants of O, but Virasoro descendants of O. And that's exactly what our formula was. And so everything that we did in the last few slides is equivalent to specifying what these correlators are. Or equivalently, if you know these correlators, you can decompose. So we have a way of computing these correlators that's based on a bunch of fairly technical things that we've done in the past. It has a fairly simple interpretation where you can use the first quantized description of some particle propagating from where phi is to where O is. You can interpret the stress tensor. You can interpret the metric as having the actual quantum stress tensor. You can compute all of the correlation functions this way, and this is equivalent to what we did. And I mention this for maybe only one reason physically, which is that this formula, if you're say an effective field theorist or something, is some fairly familiar thing. I mean, I'm computing the correlation function between these two things via this first quantized path integral. And I can do that in any metric, and I'm going to get sort of the right two-point function in that metric. So the fact that our whole prescription is equivalent to doing this means that we're guaranteed to get the right correlators in any semi-classical geometry. And that's important. I don't want to go into all the technical details, but that's how you know that this weird symmetry thing we did is equivalent to something much more physical.
Sorry, can I ask a little confused?
Please, yeah.
Yeah, about this, because somehow the previous thing, the way I understood it, sort of formally is that you chose these special diffeomorphisms that correspond to Virasoro,
Yeah.
and required that the bulk field transform correctly under those.
Yep.
Right. But here, so there, it's somehow these diffeomorphisms are at least locally not doing anything, right? But inserting these t's certainly does something locally. So.
Well, I'm not sure what you mean by locally. The diffeomorphism is doing something, right? I mean, it's a vector. It's telling you how when you act with a Virasoro symmetry transformation, it's telling you how phi moves. And phi really moves. It doesn't do nothing. Phi does. There was this very simple fact that the origin in my metric doesn't move. But if phi is not at the origin, it will for sure move. Or if you act with one of the L's that doesn't have an m bigger than or equal to 2. So general Virasoro transformations for a phi in a general place do something very non-trivial to that field. They move it around in some way.
So maybe I think maybe what I'm missing is the fact, like you said before, which is special right to 2 dimensions, is that T is in some sense entirely made of these Virasoro generators. So it is also, I mean, I understand that diffeomorphisms also move fields, but my confusion was that in higher dimensions, T also it doesn't just move things around, it inserts something. It really changes the state locally. But I guess in 2D, because T is entirely made of Virasoro generators in some sense, it doesn't. It does the same thing. It just moves things around.
Yeah.
So, okay.
Yeah, I mean, yeah. If you're happy, then I'm happy. I mean, T when it acts on the vacuum does create, I mean...
I'm always happy.
Okay, good. We're all happy.
I'm just trying to see if I understand.
Yeah, I mean, it's important to note that when T acts in the vacuum, it doesn't leave the vacuum invariant. It creates gravitons. So T, or the Virasoro generators, when they act in the vacuum, create something. But you're right that they don't create something localized at a place in the bulk. Okay. And this is, again, I mean, you can ignore this. This is just some technical thing. Just to give you an example, the simplest non-trivial correlator is phi O with 1 stress tensor. This is the answer for what we say it is. This answer is something that you can get from our prescription for phi, from what I said on the last slide, or just from a straight Witten diagram computation, like Feynman diagrams in the bulk. All of these formulas agree at the large central charge, and this is the answer. Something very technical that you'll only understand maybe if you know a lot about 2D CFTs, or at least something about them, is that the stress tensor is at this coordinate z1. You'll notice that this correlation function has a 3rd order pole at z1, but it doesn't have a 4th or a 5th or a 6th order pole at z1. I mean, no matter what you do to this function, it doesn't have any higher poles than z1. That's the sort of very algebraic reflection of this fact that Lm greater than or equal to 2 annihilates this state. The reason for this is that the action of L's on anything can be obtained from doing some contour integral of correlation functions, and the poles in the correlation function tell you sort of which L's act, and so this ends up being equivalent to the fact that there are no higher poles here. So something for experts.
You are working at large central charge, or you're not?
No, I mean, everything's exact, but I mean, this is the exact answer. It agrees, I mean, there's no non-trivial coefficient here, so I mean, it agrees with the naive bulk perturbation theory. Another super technical thing for experts is that our prescription generalizes a well-known formula for how to generate, why don't I just say it? Someone can ask me about it. Okay, so now let's talk about the exact propagator and the fate of bulk locality, in other words, the title. We've defined our operator phi. Now let's calculate its correlation functions. So the simplest sort of interesting local observable we can compute is the 2-point function. And because we have these nice definitions, we can actually compute it in all sorts of different ways. So just kinematics, we're computing phi of x, phi of y. I'm going to, for the rest of the talk, use sigma as the geodesic distance between x and y. And we'll often do expansions in a variable that I'll call rho, which is e to the minus 2 sigma. So at long distances, rho is 0. When phi of x and phi of y are right on top of each other, rho is 1.
Question.
Yep.
Is this the geodesic distance in pure ADS, or is it the geodesic distance in the metric with your non-trivial?
Good.
meshes?
This is the geodesic distance in pure ADS. So the naive interpretation of this propagator, I mean, this is the vacuum propagator, right? I'm not computing this in any geometry other than the vacuum. So naively, you would say that I'm in the vacuum, I'm in pure ADS, and then I act with this, and then I'm in the vacuum. So I think I'm in the vacuum. I mean, you could try to ask some confusing question about what's going on in between. I don't know. We're just computing the answer. But this is all in vacuum geodesic. A fact that may surprise you or may very much satisfy you is that our gauge choice made the radial direction, I mean, it made some direction in ADS special. This full propagator, the exact answer, is not spherically symmetric. So even though you're computing the vacuum, even though ADS is a spherical, I mean, if I pick a point, I have spherical symmetry on that point, an empty ADS, this correlation function is not spherically symmetric. Leading to the first two orders in perturbation theory it is, but beyond that it's not. So in general, the propagator can depend on the angle that x and y make with the radial direction, right? So we have this plane, and then there's the radial direction. If x and y are here versus there, what this angle is can matter. It's still cylindrically symmetric, but it's not spherically symmetric. So everything that I say for the rest of this talk is actually just going to be in the ZZ bar plane for simplicity. So it's going to just be expanded in this variable, even though in principle it can depend on the angle too. So now there are many different ways we can compute this propagator. One interesting limit we can take is the limit corresponding to semi-classical gravity. So we can take the limit of g Newton goes to 0 with g Newton times mass is fixed, or in CFT language we can take the limit that the central charge is large with operator dimensions divided by central charge fixed. In this limit, it turns out to be the case that this propagator takes this exponential form. It's not super mysterious why this is true, but I certainly don't have a proof. This is a well-known property of other objects in two-dimensional CFTs, but anyway, this is just, it seems to be a true statement. And there's a very, very fancy, very technical method from the study of two-dimensional conformal field theories that I usually refer to as the monodromy method that one can use to compute this function g. If you compute this function g to first order in an expansion in h over c, then you get this answer. So this prefactor is just the free field propagator in empty ADS, and this is this first semi-classical correction in the limit where basically the bulk mass times g Newton is small, and so it takes that form. But you can also do something more interesting with this semi-classical analysis. You can take the limit of very, very, very large operator dimension, or very, very large bulk mass. Not just large, but very large compared to m Planck, arbitrarily sort of infinitely large. And it turns out you can get the exact answer for the correlation function in this limit, and it takes this form, which is complicated and mysterious looking. But let me actually tell you the interesting features of this formula, or the interesting things you can do with it. So the first point, which is again another technical statement, is that this formula is very useful because it's a seed for another useful technique called the Zamolodchikov recursion relations, which give you recursion relations so you can compute the propagator exactly, not just in any particular limit. The other point, which is more physical, is this. So I wrote down some complicated formula. It was q to a power times some other stuff, where q was this thing, and this other variable was this thing. Okay, what does that mean physically? What it means physically is that this variable q, just by itself, has a branch cut starting at rho equals this exact number, which is about 0.07. What that means is that since rho is e to the minus 2 sigma, as a function of the physical separation between points in the bulk divided by the ADS length, our 2-point function has a branch cut starting at a distance scale of order the ADS scale. This is very, very, this is bad. It's not physical. It's a violation of unitarity because we're studying what wants to be a free field theory coupled to gravity. That might make you think that the field can decay into gravitons, but by symmetry considerations, by what we're actually studying, phi cannot decay. Phi number is exactly conserved in everything that we're doing here. That means that the 2-point function of phi, a real scalar field that can never decay, can't ever pick up an imaginary part. That means that if it does, when we compute it, pick up imaginary part, there is a violation of unitarity in our theory. And what we're seeing here is that violation of unitarity happens at basically the ADS scale in this weird limit that we took where the mass of our bulk field is very large. So this shouldn't actually surprise you very much. If you tried to make up, if someone told you, I have an operator that creates incredibly huge black holes in the bulk of ADS, and I computed its 2-point function, and at short distances it's non-unitary, you probably would have been surprised. You probably would have asked a bunch of questions before they even got to that point, and you wouldn't have been surprised that there was some violation of unitarity. What this is trying to be is it's trying to be a scalar field dual to an extremely, extremely large mass object, and so unitary breaks down at the ADS scale. In fact, you might be surprised that unitary didn't break down sooner. You might have thought that there's some sort of Schwarzschild radius associated with this object, and maybe unitarity should have broken down to the Schwarzschild radius, which at large mass is much, much bigger than this, but that's not what we find. So we don't see any hint of the Schwarzschild radius in this, but we do see at the ADS scale a breakdown of bulk locality. Okay, so that's all very nice. So now I'm going to tell you something disturbing that hopefully you can yell at me about. If there's a time to yell, it's now. So you can study this 2-point function perturbatively by just doing loop diagrams in ADS, like gravity loop diagrams. So this is a loop. I mean, it's a scalar propagator with a loop of gravitons. This is the kind of loop diagram that you'd expect to contribute. And what we find, we computed this loop diagram in ADS3 in our gauge, and we find it exactly agrees with our prescription. So that's very nice. However, this loop diagram and our prescription have a strange feature. So if we look at this, this one loop correction, and I've written it in terms of physical units in ADS, sigma is the physical separation between these 2 points, remember. This is the first G Newton or 1/c correction. So you see that at short distances, where these things get very, very close together, it goes like G Newton R-ADS cubed over sigma to the 4th as a correction to the free field result. And then there's this other correction, which is G Newton M squared R cubed over sigma squared, and then there's some higher stuff that matters much less. Now, why should you be disturbed by this? Well, R-ADS is some sort of IR length scale. I mean, this answer is finite. There's no IR divergence. However, R-ADS is an IR length scale, some sort of long distance scale, as we take sigma to 0. I mean, we're taking sigma to be very, very small, very much smaller than the ADS scale. In general, in effective field theory and quantum field theory, we don't expect to have UV-IR mixing. In other words, we don't expect to have an answer that's like an IR length scale to some power divided by some UV length scale to a power. That's a weird sort of surprising thing that shouldn't happen in local quantum field theories. But all indications are that it happens here. What that means is that there's some new length scale that I didn't expect that emerges from just first order perturbation theory. I don't think anyone's ever computed this before. I mean, you would probably know, but I don't think anyone's computed this. So, but someone could have and found the scale. But anyway, there's the scale sigma star, which is the 4th root of G Newton R-ADS cubed, which is sort of the natural scale at which this factor becomes order 1. And this should surprise effective field theorists. It means that there isn't really a good flat space limit of any of this stuff. In flat space, you'd want to set R-ADS to infinity and keep the other physical scales fixed. That doesn't seem to exist here. Now, of course, you could just say, I don't care about flat space. What I care about is ADS CFT. This is finite in ADS, and so it's fine. But if you're going to yell at me, you should yell at me or comment on this.
I'm not going to yell, but my comment is, so this is somehow, this just reminds me of these, if you these theories like massive gravity.
Yeah, they have some intermediate mixing scale,
So I was just trying to think, is there any, somehow, yeah, but I mean, if you say that this is the answer you get just from bulk perturbation theory.
Yep. In this gauge, I mean, it's
gauge,
possible that if you chose a different gauge, you'd get a different answer. But in this, I mean, I can even tell you sort of why is this such a high power short distance singularity? It's because the graviton propagator in this gauge is just the CFT 2-point function, literally. So the graviton propagator is just like 1 over Z1 minus Z2 to the 4th. And so at short distances, this is blowing up, and this is effectively, I think this is what translates into this sort of blowing up at short distances. And I mean, I believe that if you go to higher dimensions, this certainly doesn't happen. I think that you get the naive thing you'd expect from dimensional analysis. I don't know, I mean, maybe people in the audience know something about how ADS3 gravity is supposed to map to flat space gravity. I don't understand 2+1 dimensional gravity in the flat space limit very well at all, in flat space. I don't know that if anyone's ever computed a loop diagram in it, but this seems to suggest that if you computed a loop diagram in that theory and you tried to use something that was mimicking our gauge, which maybe is hard to do, then you should get some IR divergence that's really bad. You should get some power law IR divergence.
Is there some way to check to see whether this could be just purely a gauge artifact? Is there some gauge invariant quantity you could compute where if the singularity were a gauge artifact, it would cancel out?
I mean, I don't know what you mean. I mean, you have to fix. This is a bulk observable at some point in the bulk, so you have to fix a coordinate system.
I know.
You can ask, is there a nice?
I don't know how to.
Yeah. You can try to choose a better coordinate system where this doesn't happen, but I mean, it would have to be obviously a huge modification of ours at short distances. I don't know what that means. These are all good questions. I mean, usually people would say there's no propagating graviton in this theory, but I mean, there is a graviton 2-point function, and that's what you do to compute this loop. This also matches. There's a unitarity argument for this. We can compute it a different way. We can say I'm going to cut this in the middle and think of it as a sort of graviton state plus the scalar state, and we also computed it that way, and it also gives this answer. But that's sort of summing up all of the intermediate states explicitly. Okay, so Liam and I have argued about this anyway. So this is a confusing point, but now everything's going to sort of follow from just accepting this as the answer. So maybe there's some different gauge, maybe there's some sort of new way of defining the observable that gets rid of this. If that's the case, then what I'm going to say the rest of the talk will not necessarily be true. But let's just take this seriously. So now I'm going to tell you what the answer is to all orders in perturbation theory in the short distance limit. Turns out that using fancy CFT techniques, the Zamolodchikov recursion relations, you can learn that there seems to be an exact formula at large central charge, and as you take the short distance limit, this sigma goes to 0. So this quantity didn't just appear to first order in perturbation theory, it appears to all orders in perturbation theory in a natural way, and you get a divergent asymptotic series in this quantity. What happens with this? Well, this is a divergent series. It's a very simple one, though. You can either Borel resum it, or you can observe that it satisfies some differential equation, and you can solve that equation. Either way, there's a pole on the real axis of the Borel plane, which generically is usually interpreted as saying the answer is just non-perturbatively ambiguous. Generically, if you choose any resolution to that ambiguity, you get an imaginary piece at short distances, which, again, by the same argument as before, means that there's some sort of breakdown of unitarity. But we can do better than this all orders thing. We can just compute the exact answer in a different way. So there are these things called the Zamolodchikov recursion relations that allow you to compute the answer to this exactly to very, very high orders in this small variable rho. Rho, remember, is e to the minus 2 times the geodesic separation. So this is a long distance expansion. So we have the exact coefficients numerically, and we find that numeric evidence, which, I mean, this is an example of that, that the coefficients in this row to the n expansion grow exponentially, which means that the series diverges at some rho star, e to the minus 2 sigma star. And we find that numerically, this short distance scale on which the correlator diverges is something that scales like a power law, a negative power law in the central charge. That power law should have been exactly 1/4. Numerically, it looks like it's between 0.26 and 0.29. I would have liked to just say it's exactly 1/4, but it seems systematically slightly bigger than that. That may just be a relic of the numerics, but that's the answer. So we did some numeric, I mean, this is some fit. I mean, we computed, we studied 30 different values of C ranging from 1.5 to 100,000, and we extracted the way that the series diverges, and we turned that into this extraction. So what this means is that from the all orders result in the last slide, you might have thought, well, it's ambiguous. Maybe unitarity is violated, maybe not. I don't really know. This seems to say unambiguously that there's some distance at which this expansion just diverges, and the propagator just develops a singularity or a branch cut or both. And we think it's a branch cut. We don't know for sure. So it seems like at a distance scale set by either c to the minus 1/4 or something slightly larger than this numerically, physics breaks down. Now, like I said, this should surprise you. These all orders perturbative and numerical results seem to imply that bulk locality breaks down at this intermediate scale in the bulk. At this, if you probe the correlator at this scale, you find some order 1 unitarity violating piece, it seems. But it's a non-perturbative thing. I should stress, if you compute this to any order in perturbation series, to any order in perturbation theory, you get this. This doesn't have an imaginary part. It's exactly real, but there's some branch cut at small distances. So in perturbation theory, just like in field theories you know and love, everything looks healthy, but non-perturbatively there's a violation of unitarity. We don't know why this scale shows up. It's because of this UV-IR mixing. I would have been very happy if this was just G Newton, in which case this would just be the Planck scale, and you'd say locality breaks down at the Planck scale, but here it's breaking down at an intermediate scale. An amusing fact is that if you study string theory, I believe it's true that in all string compactifications, the string scale is always bigger than this.
So I'm sorry, I'm just confused conceptually. So all this is, sorry, maybe I just lost track of what you were doing. But
okay.
The scale originally emerged from what was simply a one-loop calculation.
Yes.
And there, it seems that you're not trying to say that at one loop or are you trying to say that at one loop in ADS3 perturbation theory, you see evidence of a new physical scale? Are you saying that, or would you not say that?
At one loop in ADS3 perturbation theory, you see evidence of a new scale. You don't know what that scale means or what happens there. When you then use these fancy things to compute the exact answer, you see evidence that locality breaks down at that
somehow
scale.
I guess what I want to say is that why wouldn't the interpretation be, well, look, I know that there's not some new scale at one loop in perturbation theory, and so it must be a gauge artifact there. And then the fact that I see it in the exact thing, it must be a gauge artifact there as well. I mean, it's not a solid interpretation. I mean, it's an interpretation or a, yeah. I mean,
that's why I said the slides from here to the end assume that this is actually just the physical answer.
Okay, I'm just
yeah. So those are I mean, that is what we would say. What we say is that when you compute this.
Doesn't that make you suspicious? Because somehow,
as soon as you compute,
that it can't. I mean, don't you sort of know that there can't be any new scale, physical length scale coming in perturbation theory?
I mean, that is the question. I mean, I don't know what you mean by you know that. The expectation is that no such new physical scale should come in. This is a direct indication that it does come in. I would say that once you find this result, which, I mean, first we did more fancy things, and then we were like, oh, wait, it seems like even in perturbation theory this is weird. Once you see this problematic perturbative result, you can either try to find some new observable or some new gauge or whatever that gets rid of this feature, or you can just see what happens if you assume this is the correct answer. This, as far as we can tell, this is really the correct answer in the gauge we chose.
No, I'm not doubting that.
But,
I'm
so
wondering,
yeah,
like,
yeah.
what about if you just did something like, would this effect completely go away if you started looking at boundary correlators? Because those are, you know, real.
Boundary correlators, phi in the boundary is completely trivial, right? It's just a 2-point function. It's just the CFT 2-point
It's already
function.
been designed to reproduce.
It reproduces every boundary observable you could want. I mean, you can, so you could ask, yeah, I mean, maybe something that I can mention, I mean, this is a sort of fancy, this is a more technical thing, but you recall that we defined phi itself a while ago via this expansion in Y. So to any finite order in Y, I don't think that you're going to see this effect because you're just going to be computing the correlator of some local, I mean, it's a local operator and another local operator. Acting with it on with some Virasoro generators doesn't, I mean, it just means that it's the correlator of two descendants. So to any finite order in Y, I don't think you see this. We compute the correlator sort of to all orders in Y, in effect, and then we resum it and we get some exact answer. I mean, you have to do that resummation just to see that it's a function of the bulk separation and not a function of Y, right? I mean,
Right.
there's some nice things that happen that the sum over Y1 and Y2 for phi 1 and phi 2 have to be turned into just a function of geodesic separation. It's only sort of after all of that happens that you see this new effect. So there's no way of taking phi to the boundary and sort of understanding it from that point of view. I mean, maybe another way of saying it, I mean, I told you that you can compute this by unitarity also. So what that means is, and sorry to jump around so much, I wrote down this formula. This formula is the correlator of phi with O and T. So in order to change this answer, you have to tell me how to change this correlation function so that I get a different decomposition of phi into descendants of O and Virasoro generators. Because this is the correlation function, that's all you need to know to decompose phi into these things. Then you sum over all of those things by a unitarity, and that's how you get this perturbative result. So it sort of is, it's at the most basic level of this thing. And like I said, this thing is just what you get from also some dumb Witten diagram calculation. It's just a tree-level computation in ADS where you have phi, O, and T, and you just... So, I mean, I agree, but I agree that this is very surprising, and but I don't know what I'm supposed to change. So anyway, I think that's basically it. So there's these numerics, it's a new scale. So we've defined some exact bulk field via a gauge choice. There's this violation of unitarity at short distances, also at ADS scale distances if the mass is very large. And we next want to try to understand this issue. Is there some other choice you can make where you don't get this UVIR mixing? Or should we just use this object to compute correlators and black hole documents?